we're on Module 9, so labs 18 and 19. Y'all have a page number there? Okay. So we're looking at probably one of the most of the classic chemistry deals. Y'all know about this already. You just don't, maybe you don't know that, but we're learning about acids and bases today. All right, so we're going to be looking at what is an acid, what is a base, and then why is it important in chemistry that we know about these things. All right, so an acid. This will be your first set of blanks. Characteristics include they taste sour, but there's a note, never taste anything in chemistry class unless I explicitly tell you to. If I say you may taste this, but don't taste anything else. They are covalent compounds that conduct electricity. So that's kind of weird, right? Because normally, what do we think about when it conducts electricity? Ionic compounds, right? So here's a covalent compound that conducts electricity when added to water. That's one of the things that makes them useful and unusual, I guess. And it turns blue litmus paper red. Blue litmus paper, we're going to talk about that in a second. Litmus paper, basically, it looks like this picture over here. It's paper that's been impregnated with a chemical, and the chemical is sensitive to a change in acidity and alkalinity. All right, so another name for a base would be an alkaline, but we just call them bases. So, but that's what litmus paper is. So if I have blue litmus paper and I touch it to an acid, it will turn pink. It'll turn red. Okay. Bases. So what is a base? The characteristics are they taste bitter. I will tell you that often the things we're using in chemistry that would be considered a base that would taste bitter were things that would also poison you. So once again, don't taste anything until I ask you to. Furthermore, does anybody really like the taste of bitter? Now, I'm drinking tea right now, and it's interesting. It has a bitter taste, but it's very acidic, it turns out. So is coffee. Bases are slippery when dissolved in water. You may have, if you ever helped with the laundry and you were using some Clorox or something, and you felt something slippery on your hands after that. That was the Clorox. You need to wash that off immediately. It's very slippery. And it turns red litmus paper blue. So when we compare the two right there, there's our acid on the top. A lemon would be acidic. It tastes sour. We know lemons taste sour, right? They do react with some metals right here. It's talking here about conducting electricity. A base, look, it tastes bitter. Have y'all ever tasted soap? Some of you may have tasted soap back when you were younger, right? You got your mouth washed out. It's bitter, bleh, right? We don't like the taste of soap. It turns red litmus paper blue, and it's slippery to the touch. We know that about soap. Soap is slippery, right? And so soap is an interesting deal. We use that to clean things, and oftentimes the things we're cleaning are acidic. The stains are acidic, like this grass on your knee, on your jeans, that's acidic. And so guess what's going to help clean it up? A base, soap. Yeah. All right, so but what's the chemistry? What's happening with the chemistry here? Okay, I can tell you all those characteristics of acid and bases, but what makes it chemistry? Well, what happens is with an acid, when it gets into our water, that hydrogen will dissociate from whatever it's attached to, and it will also give away its electron. So let's remember about hydrogen. What's its atomic number? 1, which means it has 1 proton and 1 electron. Now, if it gives away that 1 electron, then what is left? 1 proton. Okay? So a hydrogen atom without its electron is essentially a proton. So that proton that gets kicked off, that's what makes something acidic. That little H plus right there, that's a hydrogen ion, positively charged. It's a proton. And it makes that anything that lets those off of it, when it gets rid of it, when you put it in water, is considered an acid. Meanwhile, a base, anything that sends out typically an OH, so that would be a hydroxide group. Remember, that's a polyatomic ion. A hydroxide group, that's going to be our base. Now, hydroxide isn't the only base that we work with, but so that's just typical right there. But what's going to really happen here is that hydrogen plus, that proton, is going to actually attach to whatever let go of the OH. So that means it's going to take the proton. That's what makes it a base. All right? We'll get to some more detail on that. What is an indicator? An indicator is a substance that turns one color in the presence of, in this case, acid, versus another color in the presence of a base. Y'all remember back in earlier science classes when we used something called Jiffy Juice, red cabbage juice, and it would turn colors? We might use that next week, in fact. I'm using it this week with my biology students, and we're going to see how it changes color. But we also have a really, really fun indicator we'll be using next week called phenolphthalein, which is the classic acid-base indicator. But Jiffy Juice is a really nice one. You can make that at home. You get a red cabbage, cut it up, boil it, use the water, and it's purple, and you add some vinegar to it, it turns pink, magic, right? I do that for my grandkids. They think I'm a magician. All right. There are other indicators out there that indicate other things. For instance, we know that iodine indicates the presence of starch. We've done that before, right, where it turns black in the presence of starch. Okay, that's an indicator. We're just talking about acids and bases right now, so it turns out we're talking that indicator in relationship to acids and bases. Okay, so phenolphthalein being the famous one, and then cabbage juice being another one. So this is called pH paper. Next week, I believe, I've got the red and blue litmus paper, but it's not as useful as pH paper. Has anybody ever tried to keep the chemicals in a pool? Yeah, try to keep that up, and you use, paper's not sensitive enough. I mean, it'll show you generally what the pH of your pool is, but around here it turns out our water, you made this very alkaline, and so we have to add acid to pools. Do y'all know that? We have to add lots of acid. Not just chlorine. Chlorine's a base. Chlorine's killing the bugs that are in there. So we have this basic water, when I say basic, I mean alkaline, not acidic. We add more base to it with our chlorine, unless you're using a salt pool, but chlorine is what we put chlorine in our pool. And then we have to add all this acid in there, very strong acid, in fact. It's called muriatic acid. It'll burn a hole through your deck if you're not careful, yeah, but anyway, pH paper will give you a range of colors. It's really very useful versus the litmus paper. Like if I have a lemon, and I'm gonna have to touch it with two pieces of paper, the blue and the red, to see which one changes. So on the lemon, what's going to change colors? Which paper? Y'all wrote it down. Which one?
With the lemon, it'll turn red.
So the blue will turn red? Mm-hmm. But what if I take the red and put it on there? It won't do anything. Mm-hmm. So essentially I'm wasting a piece of my red litmus paper. Where if I do this, it'll give us a range of the pH. So I think we're going to use pH paper. So let's talk about what that pH means. Now, you've heard pH all the time, balanced pH, all over the place, right? So that little p, now this is simplifying things a little bit, okay? But essentially it means the percentage of, guess what? Hydrogen ions, protons. That's what that H is for. The H is standing for hydrogen, all right? So we're looking at the percentage of the hydrogens that are present. If I've got a lot of hydrogens present, I'm looking at an acid. If I have very few, then I'm looking at a base. If I have a lot of OHs, or whatever base I'm using, it'll be another on the other end of the scale. So the pH scale goes from 1 to 14, and I believe at the beginning when they started this deal, it was arbitrary that they made the acids the low numbers and the bases the high numbers. Because if I tell you that something's very acidic and I tell you it's a 1, you're thinking, oh, it doesn't seem that. Well, it's because it goes both ways, all right? Right in the middle at 7 is neutral, and anything to the left is going to be 1 through 6 is going to be considered acidic, and anything 8 through 14 is going to be considered basic or alkaline, okay? For every unit of change in the pH, it's times 10. So it's actually a wild swing, and that's why pH paper is not good enough for pools. Pools, you need to do the chemical, you drop it in there, you shake, and you do this, and even then, you might question whether or not your pH is accurate. Because you're working with this giant thing of water, and you have to have really sensitive testing for that. All right, so with the pH of 3, a substance is 10 times more acidic than 4 and 100 times more acidic than 5. See, so 10, 10, 10, 10 multiplied. Okay, so it gets really big swings there. pH of 7 is considered neutral. Let's watch a little video about it. Short.
When water dissociates, it breaks apart into an equal number of hydrogen ions and hydroxide ions. In contrast, when other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions as it dissociates. In sodium hydroxide releases more hydroxide ions. Depending on its concentration of hydrogen ions versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it's classified as a base and releases a greater concentration of hydroxide ions. The more hydroxide ions that are released, the more basic the substance is. Bases tend to feel slippery and are often used as household cleaners. Milk of magnesia and ammonia are both common bases. When a substance has a pH of less than 7, it's classified as an acid and releases a greater concentration of hydrogen ions. The more hydrogen ions that are released, the more acidic the substance. Acids tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acids.
All right, so if you notice that we talked about over on this side, I'm going to write on the board up here to the left, I'm going to put my H plus, and then my hydroxide over here, my OH minus. Now, when I have two H's and an O, what do you think of? H2O. All right, so H2O is going to be important as we move on through this. I do want you to understand, though, that OH doesn't have to be there to be a base, okay? That's just the most typical of the bases with the hydroxide group. There are other bases out there. But when you see an OH, you know it's a base, okay? You know it's a base. And then we're going to always, 100% of the time follow our hydrogens for our acids, okay? That's always going to be the case for acids. All right. I don't know why my videos go in twice now, but they do. All right, here we go. So here's our pH scale, our neutral, our acidic this way. And I think you're supposed to write a few things down on your book right there. So put in the middle 7 neutral. You can put water there, technically distilled water, because the water that comes out of our sink depends on the water source that we have. So our water source here in the Bastrop area is a little bit alkaline, so it's a little higher pH. Unless you put it through a filter or something, that might help change by taking some of the OHs out. Notice to the right we have our bases. So baking soda, we know that from our volcanoes, right? Our vinegar reacts. Our vinegar is an acid, we know that. Ammonia, we clean with that. Lye is a cleaner. It usually is what we use to unstop drain clogs in our drains. That's because typically what's clogging your drain are things like hair and stuff like that, which is acidic, and therefore a base will go in there and unclog it. To the left, we have our acidic things. We have, look, it says normal rain, slightly acidic. If you're in a big city, you might have even more acid in the rain. It has to do with the fact that it's going through chemicals. It's coming through chemicals in the air, pollution, causing acidic rain. We have lemon juice. We have battery acid way over here. Also at about 1 is your stomach acid. It's called hydrochloric acid in your stomach. If we took the acid out of your stomach and dropped it on your skin, it would burn you. You know, so it's sitting there in your stomach to help digest your food. And why in the world doesn't it burn your stomach? It's because your stomach's so beautifully designed to withstand that acid. Some people have a problem where it doesn't, and they get something called an ulcer, a stomach ulcer. That's when the acid actually eats through the stomach. Yeah, so. All right, here's some typical acids. Lemon juice, I think that might be soy sauce. In the back there we have vitamin C, we have baking powder. Interesting, baking powder is acidic, but baking soda is a base. Never get those mixed up in your recipe. You'll mess up your recipe. We've got ammonia, we've got Drano-C, cleaning a drain right here, oven cleaner, cleaning off food stuff that's stuck inside your oven. Guess what? Most of the foods we eat are acidic. In fact, we like the taste of acidic things. You young people kind of like those sour things, like those sour gummy worms and stuff. Ugh, I can't stand them as an older person. But those are very, very acidic. All right, here we go. Strong acids. I find this interesting. White bread is a strong acid. Huh, I never would have guessed that. Alcohols, Cokes. Cokes are terrible. They have sugar and acid in them, and they eat away at your teeth. So they're bad for your teeth. Sugar, interesting. Mild acids including meat and fish, some vegetables, nuts, Dairy, look at alkaline. We have fruits, vegetables, avocados, God's gift to the planet, right? Almonds, and then strong alkaline. These would be, when you think of asparagus, do y'all like asparagus? It's kind of got a bitter taste to it, right? Because it's got an alkaline in it. I think probably Brussels sprouts would fit in that group as well. Also bitter, yeah. Peppers, I wouldn't have guessed melons, and kelp, which I don't eat. So, all right. So I have a picture up here to the right, and this is a baseball game, and there's a guy stealing a base. Okay, so we're going to use that imagery here to help us remember the difference between acids and bases. Okay, so in respect to hydrogen, okay, hydrogen is our thing. An acid donates our hydrogen plus, our proton. It donates it. So the acid loses its hydrogen ion. You get it? It donates it. It gives it away. It loses it. It's the loser. In respect to hydrogen, a base accepts it. So we're going to say steal a base. Okay, like stealing a base. You get it? All right, so that's how you remember that hydrogen ion is going to the base. There's an exchange going on here. So acids cannot do their job without the help of bases, and bases cannot do their jobs unless they have an acid to work with. So acids and bases work together. They go together. I mean, I can have an acid salad dressing. Acidic has got vinegar in it, right? And so I'll just eat that, but it'll get into my stomach, which has an acid in it, and help digest and that kind of stuff. So if I'm eating it, and not necessarily wouldn't do that, but in chemistry class, we're going to be using acids with bases every single time. All right, here we go. So here's our picture again of our hydrogen. I want you to remember that the H plus represents a proton. It's a proton. Acids destroy bases. Okay. So here we're looking at an acid-base reaction where we have something called hydrochloric acid, and we have water. We're going to find out water is very useful in acid-base reactions because it can act as an acid or a base. It's got an H and an OH. It can do either thing. Okay? It can accept an H and become H3O. That's a thing. Or it can give an H away. So here it is, hydronium ion, the H3O with a positive charge on it because it's accepted this hydrogen from chlorine, and it's left chlorine as an ion, a chloride ion. So that's the complete ionization of hydrochloric acid. And now we're going to take a look at what in the world is going on there. What do you remember about H2O? Remember when we made like models of H2O and you had to draw out? Do you remember what shape it was? Bent. And do you remember why it was bent?
No.
Those two dots at the top. Remember that they were causing it to bend away? Those unpaired electrons. Well, guess where those unpaired electrons are going? To that hydrogen, to that H3O. So remember, it had those it has the two pair of unpaired electrons. So it's going to take one of those there to the H, and then we're going to have this new shape, and it's going to be shaped based on only one set of paired electrons. And then that one, the chlorine over here is going to have our negative charge on it. So the hydrogen in the HCl molecule left its shared electron pair with chlorine, making it an H+. So it donated it. It gave it away. It lost it. This ion then attached itself to the non-binding electric pair of the oxygen, so it was stolen. The new polyatomic ion, H3O, is called the hydronium ion. And remember, didn't we add that to our little chart? Remember back when we talked about our polyatomic ions, and I said add hydronium, and then we never talked about it again? That's because we needed it here, okay? All right, so that's what's happening in our Lewis structures. Not that we necessarily have to go back to Lewis structures. Your book will talk about it a little bit. And it's just showing you where that hydrogen is ending up. It's going to go over and grab onto those electrons that are free right there. Here's our acid, here's our base, and we end up with those things over there. In general, we have an acid plus a base. I think I'll write this down. Will generally give me water. That's hooray, because if I can start knowing that the first thing I have to put down is water, then I can use whatever else I have left over to make something known as a salt. Okay, so I have my acid plus my base, and it's going to form H2O plus a salt. Some sort of salt, which is ionic, right? Ionic compound. All right. We're going to need that again. All right, this is a goofy little video. It has a little bit of sound, but nobody's talking in it. And it's going to talk about how we're going to do this. We're going to take our HCl and our NaOH. That's OH right on there. We're going to put those together. There's our HCl. and it's in water now, so it's dissociating its ions over here to our NaOH, OH polyatomic ion. We're going to pour them in together. Pour fast. Here's our sound. And now we're going to see what's happening in a goofy way. Here. All right. So now we see our H's and our OH's and our chlorines and our sodiums. So one thing we're going to make is this. So watch for that. Ooh, there's one that made it. H2O. Okay, there's our H2O. And then what are our sodiums and chlorines going to do? What are sodium and chloride going to do, y'all? It's going to make sodium chloride. So that's what happens. There's our sodium and chlorine going together as ionic bonds because they're attracted to each other, negative, positive. So you get it? All right. So special situations. Okay. This word. Amphiprotic compounds are compounds that can act as either an acid or a base. And for our purposes today, we're going to be using that in talking about water. So go ahead and write the definition, then write H2O next to it. Typically, well, I'm not going to say that. It can be water can be an acid or a base. We just already saw one where it was the base, right? It stole the hydrogen. It's typically a base, but all right. Polyprotic compounds, are acids that can donate more than one H ion. For instance, if it said H2SO4, that's an acid. It wants to give away both of those hydrogens. So polyprotic. And sometimes there's some that have with three. So there's triprotic as well with three. When ions dissolve in water, they break into their individual ions, such as sodium and chlorine. Okay, so we have to assume that we're going to put our acids in our water, and they're going to dissociate in there and in the water. Okay, the water's kind of holding them. It's sort of an aqueous, if you will, solution right there, dissolved in there. All right. This is to show how complicated it is. But y'all don't have to know this part. This might be in chemistry 2 or something, you know. But it's just showing here where the water is acting as a base in some places and an acid in some other places. Although it looks like it's a base, as an acid right there, okay? So sometimes it's acting as a base, sometimes it's acting as an acid. Water can act as an acid or a base, okay? So here we show some examples of it. It's acting as a base with hydrochloric acid. It's acting as an acid with ammonia, which I think that picture just showed on the other side there. So it's amphiprotic. Remember, in order for a substance to conduct electricity, it must contain electrical charges that are free to move. That's what ionics do, right? They separate, and there's these ions floating around in solution. When ionic compounds dissolve in water, we have that, like sodium and chloride. Now, when acids mix with water, the result is a solution where the ions are free to move. And that ion being our H plus, right? And then whatever the OH minus over there, those are free to move. So therefore, that's why they can conduct electricity. That's why water, which is a covalent compound, can end up acting like ionic right there. And it has to do with acid-base chemistry. So they can conduct electricity too. All right. Don't forget the polyatomic ions. This was from back in Module 5, I think. That could be an old number. There's 5 sound right? So these are the ones, and then I didn't add on that H3O, but we'll have to remember the H3O as well. So kind of re-familiarize yourself with these things before doing your practice problems, okay? Because if these end up, we're gonna need to know those when they separate out, that they stay together as a polyatomic ion. All right, identifying acids and bases in chemical reactions. We can analyze these equations. First, must find the ionic compound. That's why you memorized those polyatomic ions before. I said memorize. Did y'all have that memorized? One time you did, you still? But you have a chart somewhere you can look at. Did I print that chart out for you? Yeah, so pull that out and take a look at that. Split the ionic compound into its parts. Now follow the hydrogen. Figure out where does the hydrogen want to go to determine the acid and the base. If an ion does not participate in the reaction, it's known as a spectator ion. okay, a spectator ion. It's just kind of watching. We're going to see some examples of this. So we're going to analyze acid-base reactions. Now, I think you have some boxes to write some stuff down, right? Okay. So these are going to be examples. So this is example 9.1. Determine which reactant is the acid and which is the base in the following reaction. All right. Notice I don't have anything that says OH on it, which would be the dead giveaway, but I don't have that here. So I'm looking at H2SO4 in aqueous solution. That means it's floating around, therefore they're separated. And our CaCO3 in an aqueous solution. So we're going to see which one is the ionic one. Remember, CO3 was on our chart just now, right? Carbonate. And so we can split those up. We can take our calcium and our CO3 right here, and then our HSO4 negative, that takes one of the H's away. So which one gave away a hydrogen? H2SO4, which you might have already known that H2SO4 is sulfuric acid. It's a classic, it's a big one right there. Furthermore, I'll also give you another hint. We almost always put the acid first. Acid plus base equals whatever, okay? Almost always. Somebody might mix it up just to mess with you. I don't know. I wouldn't. I'd always put the acid first. It's sort of like, subject predicate, we're going to put it, in the proper order right there. So I split these two up. I'm going to see how my hydrogen's going to come over here to my CO3 right here, and then it might do it again. So notice that the CaCO3 split up, so it's not the acid, it's the ionic one. It's going to be our base. Where will the hydrogen go? So I have here the Stola base for the CO3. Let's see, it was CO3 minus 2 here, it's CO3 minus 3. It lost an H, and this one was a spectator. So our calcium was just our spectator. All right, so that's how you're going to try to guess. First of all, also look at the hydrogen. Am I going to be an acid if there's no hydrogen there? No. But if it's H2O, remember H2O could be either an acid or a base, so then you're like, oh, well, there's an H there. What am I supposed to do with that? So don't always go with the H being the acid, but often, especially if you don't have H2O as your next thing in the reaction. All right, so let's try this one. All right, so here's okay. We have a couple OHs. I'm always happy to see the OHs. Then we know we can make water with that. So hooray. So let's start at the top though. We have H2SO4. That's what we just did, right? So we know that split up the compound. We just did that one. H2SO4 lost an H, so it's the acid. CO3 gained an H, so it's the CaCO3 is the base, called calcium carbonate. It's chalk. Here we have HCl, NaOH. Can you just tell me right away which one's the acid, which one's the base? If there's an OH in it, you know it's the base. Okay, so that's called sodium hydroxide. First, split the sodium hydroxide into Na and OH. Next, split the HCl into H and Cl. And now we can see the HCl lost an H, so it's the acid. OH gained an H, so it's the base. NaOH was the base. And Na, sodium, was the spectator. Get it? Next one, you already know which one's the S and the base, yes? On the bottom? Well, you can tell me what the base is. The one with the OH in it. Yeah, magnesium hydroxide. So this must be an acid. All right, so let's see. First, we're going to split up that magnesium and the hydroxide stay together because they are polyatomic ions, right? Polyatomic ions. The most famous in acid bases, don't forget that. That's your friend. OH minus is your friend. All right, then the magnesium is alone here, so let's see if it's a spectator. Yeah, magnesium's just a spectator. It's not really doing anything. HNO3 turned into NO3 ion, and so the HNO3 is the acid. OH ion became H2O, so MgOH is the base. So those are actually kind of easier ones, and you don't have to necessarily tell me I split this, I'm split. You just say, well, this one, this is my acid, this is circle, this is my base, that kind of thing. All right, which is the acid and the base on these? So y'all tell me on the first one. Oh, it's kind of tough because I don't have an OH in there. Bummer. All right, and I have an H in both of them. So what's going on there? Which one do you think is the acid? Yeah, it's in the front. Okay, it's in the front. It's called hydrobromic acid. All right, so I don't know. They're not trying to mess you up at all, I guess. Let's see. HBr is the acid. NH3 is the base. So if HBr is the acid, NH3 must be the base. We're doing acid base here. One of them's an acid. One of them's a base.
No.
Notice I didn't end up with any water on this one and a salt, 'cause that's a little different. This is just general. This acid base equals H2O plus salt. What did I do there? That's a plus. These pluses and minuses are supposed to be up there, I guess. They got the wrong place. Okay, the next one's very easy. The next two are very easy because you know what the base is right off the bat. Okay, so what's my acid? This in the front, C, whatever that is. I need to make these bigger. My Al, aluminum hydroxide. And then look, I made H2O. Yay. I made H2O on the bottom one too. So this C2H4O2 is the acid, AlOH3 is the base. And on the bottom, same thing, right? H3PO4. KOH is potassium hydroxide. That's a classic base. Right there. So H3PO4 is my acid, KOH is the base. So I may have a couple of questions like that on there, and you have to figure that out. If I do have more than one, I'll certainly have an OH in there that'll make it easy for you, but I might give you one like that top one. We have to figure it out. But I'm going to give you a list here in a second of the classic, I think it's next up, yeah, the classic, and you're going to write them down, common acids, and then you should start to recognize those. Okay, you'll see them right off the bat. So, oh yeah, that's a famous acid. HCl is a famous acid. It's hydrochloric acid. It's in your stomach. All right, do y'all have these few problem things written down? I don't know if they're, I guess maybe they're OIOs. But remember to do your study guide. And these are all in your book, so if you can't see them very well, because I don't have them big enough. I tried to go in and make things bigger, but I obviously missed this slide. Although I just found out there's a way to make my slide bigger while I'm in the midst of this. I can zoom in. Do y'all know this? But I don't necessarily know how to go back. Oh, look, I can't do it in slideshow mode. It won't let me do it there, which is fine because I don't know how to go back. All right, you're going to write these down, I think, right? In that chart? All right, so you're going to write down that HCl equals hydrochloric acid, HBr equals hydrobromic, HF is hydrofluoric, HNO3, we saw that already, nitric acid, H2SO4, that's one, these top two are the most famous, HCl and H2SO4. H2SO4 is sulfuric acid. Those are the ones that you watch in the movies and someone throws acid on the face and they start melting, you know, unless it's Wizard of Oz, which is water. H3PO4 phosphoric acid, and H2CO3 carbonic acid. That's what's in Coke, Dr. Pepper. That's the kind of acid that's in there. And then C2H4O2 acetic acid. That's vinegar. That's what's in your salad dressing. Delicious. So always look for that H. Look how they all have H's in them. In fact, all of them except that last one have the H in the front, which is another dead giveaway for an acid. That H in the front. So acetic acid is the only one that's acting straight. So that's because it's a hydrocarbon. But so is carbonic. I wonder why they didn't put acetic acid H4C. 2O2, yeah. So you're going to just start to recognize those when you see them. I don't know if we use any. There's other acids out there. These are just the most common. Muriatic acid is one I can think of, which if I'm not, I think maybe muriatic acid might be a very strong hydrochloric acid. That's the acid we put in pools, by the way. right, and this table 9.1 is also in your book on page 324. So let's predict some reactions. A polyprotic acid, what's polyprotic? It's got more than one H. More than one H. Poly means many, protic means protons. It's got many protons. It's an acid that can donate more than one proton. H3, is that a H3PO4? Did we put that on there? Well, it wasn't even on our list, was it? Was it on our list? H3PO4, phosphoric acid? I was about to say it should have been. It's pretty.
Oh, yeah.
Yeah, it's pretty classic. H2SO4, sulfuric acid, it's diprotic. So H3PO4 is triprotic. It's got 3 hydrogens it's trying to get rid of. I've got H2SO4 is 2 hydrogens it's trying to get rid of because it's acidic. H2CO3, carbonic acid, a prediction, it wants to give away both of them. So it's going to be diprotic. Okay, so predict what's going to happen here. What's my acid and what's my base?
Hydrochloric acid.
All right, so that's not too bad. It's not even a diprotic or triprotic. It's just a single old hydrogen on there. So what we have is acid, base plus salt and water. So I don't know what fluorine and potassium, what kind of salt that is. That's a weird salt. Okay. Give a balanced chemical equation that represents the reaction between hydrochloric acid and RBOH. That's easy. We know it's the acid. We know it's the base. So HCl is the acid. RBOH is the base. And then write the chemical equation that describes the reaction between sulfuric acid, H2SO4, and NaOH, the base. All right, we're going to watch this on a video, I believe. Remember. Oh, what are we remembering? Hold on. Remember. There it is. Acid, base, water, salt. That's what we're going to see here. When we have an OH in there as our base, we're going to be making water, okay? All right, let's watch.
In this example, we will be determining the reactions that occur between acids and bases. The first reaction to consider is HCl and RBOH. Now remember the general formula. An acid plus a base makes salt plus water. Our way. We should recognize that HCl is the acid because it's got an H written out front. We should recognize that RBOH is the base because it has a metal and an OH. Now the question is, what's the salt? Well, let's think about the water first.
already got
How
it,
does
right?
the water get formed? The water gets formed because the acid donates an H+. What does it donate to? It donates to the OH minus from the base.
So now
So
what's
the
left?
H plus and the OH minus get together, making water. Now, if the acid donated an H plus, what did it leave behind? The acid was originally HCl. We get rid of the H, we're left with Cl. We get rid of a plus sign, and the rest of the molecule has to become negative. So when HCl donates its H plus, what's left over is Cl minus. So when the base got rid of its OH minus, what was left? Well, you take an OH from RBOH and you're left with RB. You take a minus away and you're left with RB plus. So RB plus joins with Cl minus to make the salt RbCl. If we look at this equation, it's now balanced. HCl plus RBOH makes RbCl plus H2O. So that's the balanced equation that represents the reaction that occurs between HCl and RBOH. Alright, well it turns out that's a relatively simple acid-base reaction. The next one's a little more complex, so let's go through it. The reaction to consider is the reaction that occurs between H2SO4
Diprotic.
and NaOH. Now once again, it's acid plus base makes salt plus water. We should recognize that the H2SO4 is the acid because it has the H's written out front, and the base is NaOH because it's a metal and an OH. Now once again, the question is, what's the salt? Well remember, water gets formed because the acid donates an H plus and the base donates an OH minus. So if I get rid of the H pluses from the acid and I get rid of the OH minuses from the base, I make water. What's the salt? Well, the salt forms from what's left over. Look at what's left over. In the acid, what's left over is an SO4. That's something you should recognize. SO4 is a polyatomic ion. The sulfate.
So notice that -2. You see where that came from? We took 2 hydrogens away. So that makes, and that's very important, right? It's very important in finishing this out because we'll be able to figure out what's on our subscript. Okay.
Ion, SO4 2 minus. Now you didn't have to recognize this as the polyatomic sulfate ion. You could have reasoned it out. Acids donate H pluses. The acids donate all the H's they have in front. So the acid's going to donate both of those H's. So you get rid of H2 from SO4 and you're left with SO4. The H's are positive when they leave, so you get rid of 2 positive signs, you get SO4 2 minus. So whether you recognize this as a sulfate ion or reason out that it has to be charged 2 minus, you end up realizing that this is the SO4 2 minus ion. Now that ion will join with the metal from the base. The base donates an OH minus. If I get rid of OH from NaOH, I'm left with Na. I get rid of a minus sign, and I'm left with Na1+. Now you could have reasoned that out, or you could have just recognized that sodium, Na, is a group 1A metal. In ionic compounds, and that's what a salt is, an ionic compound, in ionic compounds, sodium takes on the charge of 1+ because all group 1A metals take on the charge of 1+ in ionic compounds. So either way, once again, whether you recognize it as a group 1A atom or whether you reason it out, you have the sodium 1+ ion. These 2 ions get together and form the salt. How do we figure out the chemical formula? We do what you learned back in Module 8. We switch the charges and drop the signs. When we do that, we have SO41 Na2. Now when we write the equations of ionic compounds, we usually put the metal first. So the real chemical equation is Na2SO4. That's the chemical equation of the salt. So that's our final chemical reaction. The problem is at this point, the equation isn't balanced. There are 3 hydrogens on the reactant side and only 2 on the product side. So we need to balance this chemical equation. Let me rewrite it, and now let's try and balance it. We don't want to start with the hydrogens because it appears twice on the reactant side of the equation. So let's start with something else. Let's start with sodium. That appears only once on both sides of the equation. There's 1 sodium on the reactant side, 2 on the product side. So I need to get another sodium on the reactant side. I can do that by multiplying NaOH by 2. Now I have 2 sodiums on each side of the equation. The equation's still not balanced though. I now have 4 hydrogens on the reactant side and only 2 on the product side. So I've still got to work on it. Well, let's look at the sulfurs. Sulfur appears only once on both sides of the equation. But they're balanced. 1 sulfur on the reactant side, 1 sulfur on the product side. So now I have to start dealing with elements that appear more than once on at least one side of the equation. I can work with either the hydrogens or the oxygens. Let's go ahead and work with the hydrogens. I've got 4 hydrogens on the reactant side. I have only 2 on the product side. Easiest way to fix that is to put a 2 in front of H2O. Now the hydrogens are balanced. 4 on the reactant side, 4 on the product side. And guess what? Now the oxygens are balanced as well. 6 on the reactant side, 6 on the product side. So this is the final answer. H2SO4 plus 2 NaOH makes Na2SO4 and 2 H2O. Most students mess up in these equations because they don't figure out the salt properly. In order to figure out the salt, you have to remember what we did in modules 8 and 9. You have to remember how to figure out the chemical formula of an ionic compound. And just remember there are a lot of polyatomic ions in this module, so you'll have to be aware of those as well. If you can recognize those polyatomic ions, and if you can figure out the chemical formula of an ionic compound.
Okay, I'm going to quiet him down. Okay, so I want you to notice something though. Because I had a diproduct acid, that means it had 2 hydrogens. Those 2 hydrogens, we can right away say, oh, I need to make 2 waters. I need to make 2 waters. All right, so then I would have known that 2 was already there. Because I know I had 2 hydrogens to go over to my OHs to make my waters, okay? I also could maybe cheat and say, well, I needed 2 OHs. So I could maybe start there and then see if I'm balanced, okay? But like he said, this is going to be the tough part right here. You've got to remember that. But honestly, instead of having it memorized in that chart, we figured out why that this SO4 was -2, because it got rid of 2 positives. It makes total sense. That's why SO4 is -2, because it gave away its 2 hydrogens, okay? All right, so there's all sorts of little tricks to get you through here that you don't have to memorize everything. All right, what if there is no hydroxide ion? Yikes. Hydroxide ion's our friend. Okay, what are we going to do here? So here, check it out. These are all our acids, okay? We know that from the front there. But look at this. We have these. We know something about water. It's amphiprotic, right? Which means that it is going to act as a base right here, okay? So covalent bases accept only one hydrogen ion. Diprotic and triprotic acids require more than one covalent base to accept their hydrogen ions. All right, so do I have, oh yeah, I have polyproducts all through. I have 2 here, I have 2 there, I have 3 there. So now I have a little arrow pointing to my 2 H's, okay? So if I'm going to come here, if I have H2O as my base, then I'm going to be making H3O+, my hydronium ion, okay? So we already know that. So then what's left over? My SO4 right there. So notice that 2 right there. I'm giving away 2 hydrogens. Therefore, I'm going to have a -2 on my SO4. Do you get that? Also, that 2 is telling me something else. I need a 2 right there. Voila. Magic. It's a trick. Okay? So if I said that way, here I have a 2 and I see my -2 over there. What's going to go right there? Look at it. What is it? It's a 2. On the last one, what is it? It's a 3. Get it? So it's a little hint there for you. So you might think, oh no, I don't have a hydroxide. Actually, it's kind of easy if you do this little trick, okay? Because you don't have to do all that crazy stuff, especially if I've given you the whole equation right here. Now, it may ask you to put these on here, but we know it's 3. We know it's -3 because I gave away 3 hydrogens. There it is. Voila. A covalent acid reacts with a covalent base to form 2 or 3 ions, depending on if it's di or triprotic. All right, this is 9b. You can turn over to 9b now. We're looking at concentration of solutions. Let's talk about concentrations.
Acids and bases are everywhere. They're used to make foods, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides, even paper. Our stomachs are very acidic. Our blood is slightly basic. Our proteins are made up of amino acids, and the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules, acids and bases were defined by how they behaved. Acids tasted sour and corroded metals. Bases felt slippery and could somehow counteract acids. When molecules dissolved in water interact, they're exchanging 2 main currencies with their surroundings: protons, also known as hydrogen ions, and electrons. Depending on how a molecule is composed or shaped, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has 2 protons but is generous enough to hang out with just 1. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules has exchanged currency with water. As you might guess, we label these acids and bases weak. But in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, that is a weak base. So it doesn't take much to be an active player in the chemical economy. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And when a proton deposit customer, that's an acid, and a proton withdrawal customer, the base, shop at the same time, their net effects on water's account may cancel out, and we call this neutralization.
So we're going to be concentrating on neutralization here. That's what we do when you make your little volcano and you put your vinegar and your baking soda and it bubbles out, then it ends, and then it doesn't smell like vinegar anymore. It's because we just neutralized it with a base. We neutralized our acid with a base. All right, this is just some repeated slides because this is part B, so we're refreshing our memory on this. Water can act as an acid or a base. It's called amphiprotic. So, water is an amphiprotic compound that can act as an acid or a base. That's a blank you're filling in. This is all review, by the way. In a previous lab or a previous lecture 10 minutes ago, we discussed the reaction between a covalent acid reacting with the ionic base, forming an ionic salt and covalent water. Here it is. Acid plus base equals H2O plus a salt. So I think you're just filling in ionic salt. Water will act as a base in the presence of an acid. It will also act as an acid in the presence of a base, right? It can do either. There's a different result when a covalent acid reacts with a covalent base. 2 ions are formed, and really that should say 2 or 3 ions are formed, depending on if it's triproduct or diproduct. All right, so you got those blanks filled in? Easy breezy. Okay, so let's analyze these. What's going to happen in part 1? It's interesting how I put that 2 there already. Okay. H2SO4, 2H2O is going to give me what? What's H2O acting as? But what is it acting as in this equation?
Oh, acid.
A base. This is my acid. H2SO4 is sulfuric acid. So this is acting as a base. So what's going to happen? Let's see. H3O positive and SO4 minus 2. There's that 2 right there. There's also that 2 right there. Get it? But then I had to come back and balance over there apparently. Okay, HI, hi. Hawaii, right? And H2O, what's going to happen here? We're going to donate that H here. And we're going to have that I as an ion over there. Okay? We're once again looking here where OH is not our base. So here we have NH3 as a base, which actually it's ammonia. It's a strong base. Ammonia, we use that for cleaning stuff, right? That's a very strong base. And we have our strong acid right there. We're going to have our NH4, because I brought that 4 over there, but I did it 3 times. That 3 comes from there. And that 3, I'm leaving PO4 together is my polyatomic-on. See that negative 3? It came from right there. It got rid of those 3 hydrogens. Y'all seeing it? Is it making sense? It's not too bad. So don't panic when you don't have a OH for your base. So probably you would have gotten everything except the coefficient. Well, maybe not. I don't know. Maybe we give you the coefficients. I'm not sure where this problem came from in your book. Reactions between acids and covalent bases. So we just looked at that. Water is a covalent base. All right, let's see what it is. When an acid reacts with a covalent base, 2 ions, sometimes 3, are formed. Okay, covalent bases accept only 1 hydrogen ion. Diprotic and triprotic acids require more than 1 covalent base to accept. This is all review. What reaction occurs between H3PO4 and NH3? It's triprotic, so we're going to do it 3 times. We're going to add it over here. Our H is going to come over here 3 times. Since the acid wants to donate 3 hydrogen ions, but the base can only accept 1, we have to run it 3 times. So what we're going to say is we're going to do it 3 times. There's our H coming over there. And then we have our PO3 left over. And we see our 3 is there, our 3 goes there, our 3 goes there. And then we have to balance that 3 out there. I'll review. of what we just talked about. Okay? I don't know which one. Example 9.3. Okay. We're trying to get to the concentration now of acids. Some acids are more concentrated than others. You may know that. Your vinegar in your salad dressing doesn't burn a hole through the table. And fortunately, it doesn't burn a hole through your stomach. It's good. Tastes delicious. All right, so we're going to the, oh, here we go. See, my 3 goes there. I just showed you my 3 where it came from. But I could do that balancing it out as long as I knew that my NH4 resulted as my salt. All right, there's our new information now. Molarity. Molarity. Not to be confused with moles, but it has something to do with moles. Okay, remember moles are our friend, right? Okay, molarity is the concentration unit. It's a concentration unit. It tells how concentrated something is. All right, how many moles of a substance are in 1 liter? Okay, right here I said write this down. I think you have a box for it. M from molarity equals moles of solute, the thing being dissolved, into liters of solution, the stuff doing the dissolving, almost always water. Okay? It tells you here that you need to have moles. You'll have to go over and convert to grams to make it sense, but you'll always have to go back to moles to make this equation work. So notice this equation is using moles and liters. Moles and liters. So if I've given you grams, you're going to have to convert to moles. And if I've given you milliliters, you're going to have to convert to liters. Okay? So let's go ahead and write this down on our board too. Okay, so M equals moles over liters. And we're going to do some math problems now. Hooray! Let's watch a little video first.
Have you ever noticed that Kool-Aid at summer camp tastes weaker than the Kool-Aid that you might mix at home? Camps have a tendency to water down the drink mix and make a more diluted version than what the mix might call for to stretch their money. Solutions with relatively more solvent and less solute are called dilute, while solutions with more solute and less solvent are concentrated. In this diluted Kool-Aid, there aren't very many particles of Kool-Aid, the solute, relative to water, the solvent. The solute is the chemical that's dissolved, and the solvent is the chemical that does the dissolving. In this case, it would probably taste better if you added more Kool-Aid powder and made a more concentrated solution. To measure concentration, chemists use molarity. Molarity is the number of moles of solute dissolved in a solution, and we use the capital letter M to represent it. You calculate molarity by taking the moles of the solute and dividing by the liters of solution. Instead of writing units as moles per liter, you just write a capital M for molar. Let's try an example. What is the molarity of a solution with 0.70 moles of solute and 250 milliliters of solution? Molarity is moles divided by liters. This problem gives us the 0.7 moles of solute, but the solution is given in milliliters, not liters. So we need to convert milliliters to liters by dividing by 1,000. Then we can use that number in our calculation. Do the math, and you get 2.8 molar. Solutions can have much lower concentrations than this, but you don't often see concentrations higher than about 18 molar. Sometimes, for shorthand, concentration will be written in brackets without the letter M. This is what it looks like.
All right, we'll be using those brackets a lot and as we move on through the rest of the year to show you that molarity. Okay, so practicing with molarity, they're just simple math problems. It's not a problem at all. It's easy. Okay, so let's take a look at it. Here we go. Find the molarity of NaOH, so sodium hydroxide, if there are 2.6 moles in a solution of the volume 534 milliliters. Okay, so first of all, we know there's a problem. It's milliliters, right? We got to make that liters. But is it easy to go from milliliters to liters? Mm-hmm. You don't even have to do your, I think I'm going to go ahead and do it. Take my 534 milliliters over 1 and do my conversion. What do we call that? Factor label. I'll do that here. But we know it's okay. Just move that decimal point, right? Just move that decimal point. All right, so we 2.6 moles, so that's good. Hallelujah. we got that, was given to us in moles. That's what we need. There's my 0.534 liters I didn't. So it's 4.9 molar. That's my answer. 4.9 molar. Oftentimes when I bring acid here to the hydrochloric acid, it's 1 molar. 1. So it's very dilute, right? It's very weak. That's because we don't want to burn holes in tables and clothes and skin. All right? A student dissolves, 124.3 grams of HNO3 in enough H2O to make 250 milliliters of solution. What is the resulting molarity or concentration of the HNO3? All right, so that's our nitric acid, right there. But I have a problem. I have two problems. I have milliliters, well, that's easy to deal with. Make that to liters easily. But I've got 124.3 grams, so I've got to convert that to moles. How do we do that? You've got to have your periodic table, and you're going to go look up each one of those things and see what their little number is at the bottom, yes? You're going to add those all together. You're going to make sure you count those 3 O's right there. So we get their molar mass from the periodic table, your best friend. 1 mole of HNO3, it turns out it's 63 grams. Okay, so we add those numbers together, we get 63, okay? I didn't show them to you right there, but it's okay. So therefore we know that 1 mole of HNO3 equals 63 grams of HNO3. Now I need to convert from grams to moles, correct? So what do I take? I take what I know, 124.3 to put it over 1. Oh, and then I put my relationship here so that I'm going to scratch out grams and end up with moles. So I end up with 1.97 moles of HNO3. Do you see how we got there? Okay, you know how you got that number. 63 came from the periodic chart of the elements. You had to add up each one of those on there. Anne Marie's adding them, were you right? 63 was right? Good, okay, good. I don't have my chart out. I'm assuming that the book was correct in doing that. All right, so now I have my 1.97 moles of HNO3, and now I'm going to put it over 0.250 liters of the water, right? Here it is, right over here, over 0.250. It has OO, must be a significant figure situation. 7.8 molarity. 7.8 molar is how we say it, molar. The molarity is 7.88. It's 7.88 molar. All right? So I think that's probably the most difficult. We're going to do a couple more of these because these are the most difficult in the module, but it's not that bad, especially if you've been practicing on going from grams to moles. Okay, if you practiced enough of that. Okay, practice concentration. This is kind of like OYO 9.7. It's a little different, but you can put it in that box that's 9.7. I have 6.78 grams of potassium hydroxide, KOH, to make 150 milliliter solution. So we know we're going to have to do some conversions, right? We're going to have to fix everything. The 150 milliliters easy, but we're going to have to go to our KOH and find out the moles of that, all right? So I'm going to convert to moles and liters. Molar mass of KOH here, I did write it out for you this time, 39.1 plus 16 plus 1.01, that's my K, my O, my H equals 56.1 AMU. Therefore, I know 56.1 grams equals 1 mole of KOH. Now I can take that and figure out how much I have by taking 6.78 grams, putting it over 1, doing my conversion based on what I just did right here, my 5.61 grams per mole, and I get my 0.121 moles of KOH. Everybody see how we got there? Okay, it's just step by step, right? Step by step. Now that I've got moles, I'm going to put it in my molarity equation right here, m equals moles over liters. I do have to change that, there it is, converting 150 to 0.150 liters. I put those over and I come up with 0.807 molarity. Molar should be the way we say it. 0.807 molar. So you'll have several other of those in your book, some other OIOs, and do those practice problems. I'd recommend that. So it's not that bad. It's really building on what you already know, right? But then we're seeing some fun stuff happen with neutralization and stuff like this. Okay, now we're going to be looking at dilution and concentration now. Okay, adding water to a solution. water to a solution in order to decrease the concentration. Okay, so I've got something too concentrated. I want to make it more dilute. I want to dilute it because my lemonade is too strong. My boys make lemonade really strong, so much that there's lemonade powder floating in the bottle. You know, it's really strong. And so if you add a little water to it, it will dilute it a little bit. Oh, maybe it's people in the other room. All right, our dilution equation, you have this written down for you. M1V1 equals M2V2. What do those stand for? M1 is the original concentration, molar, my original concentration. V is our original volume, liters, equals my desired concentration, M2, and my final volume, V2. All right, it's not bad at all. It's just directly related. A chemist wants to dilute 12.0 molar HCl to make 500 milliliters of a 3.5 molar HCl solution. All right, so we have 3 of the 4 things we need, yes? We have a molar here, that's our M1. We have our molar here, that's our M2. We have our 500 mils to make it, so it looks like our V2, yeah? There it is. We're missing our V1. So do you see what I did here? I have my M1 is 12.0 molar times V1, which I don't know, to make my 3.5, that's much less concentrated, yes? And I'm going to have 500 mils. We're going to probably, I don't know if we have to switch that to liters. Probably so. Oh, apparently not. I can stay in mLs right there. All right, so I'm going to take that, do the math, do the algebra, move things around, and I end up with 1.5 times 10 to the 2 milliliters. I'm okay with whatever, 1,500 or whatever it is. So that's just a dilution equation. Part 2. A chemist takes 2.5 liters of a 5.6 molar sodium hydroxide and dilutes it with enough water to make 10 liters. What is the new concentration of the NaOH? So M1V1, we're going to take our numbers, 5.6 times 2.5. We're going to try to find out our new molarity right there. We put our 10 in over here, which we know. So it's just plugging the numbers in a very easy equation, a simple equation. It's a word problem, just make sure you know what's what. We do the math, we come up with 1.4 molar. They were both in liters. If one of them had been milliliters and one of them had been liters, so as long as they're the same, I guess we can do it that way, okay? So, but we would have had to convert if one had been mils and one had been liters. Okay, those aren't too bad. All right, 750 milliliters, there's a milliliter, of a 3.5 molar solution of H2SO4, that's sulfuric acid. 10 molar, how to make the solution. We want to make it 10 molar, so we're going to we're trying to find our V2. How much? We need 262.5 milliliters of water to bring it down to a 10 molar. Oh, that's what we did to bring it down to a 10 molar? Because that's higher. So we're just plugging them in. I didn't put enough of the question in here. Sorry about that. Okay, here we go. This is something y'all are supposed to do on your own. A chemist has a stock solution that is 6.78 molar of hydrochloric acid. He wants to make 500 milliliters of a 1.15 molar hydrochloric acid. What should he do? That seems pretty straightforward. So y'all try it real quick on your own. Anybody have it yet? Anybody got it? I'm pretty sure I have the answer next. I hope I do. We'll see if you're right. Okay, so let's see, yeah. So we're using that, yeah? How are we doing so far? Good? Then we're just going to move things around. Is that our answer? He should take 84.8 milliliters of hydrochloric acid and fill with distilled water to make 500 milliliters. Ooh, yeah, so you get that? Interesting. All right, did y'all get it? 84.8 milliliters, yes? Okay, there you go, then you're ready. Very important. Now this is fun, y'all, believe it or not. I'm using the word fun when speaking about chemistry. Number of moles divided by volume in liters, you get molarity. We know that, okay? Number of moles divided by liters, you get molarity. That's concentration. When molarity is multiplied by volume by liters, you get the number of moles. Obvious, it's just algebra, right? But it's pretty cool. So numbers of moles of the solute equals M times V. You want to write that down somewhere? Moles equals big M times V. Big M being molarity and V being volume. All right, but this kind of makes for kind of a fun deal when we can do that. So let me write this down real quick. If M equals moles over liters, then moles,
It has it in our book.
oh good, equals M times V. I'm doing that for me. Okay, so remember the steps when using stoichiometry. Write and balance the chemical equation. Calculate the number of moles of a limiting reactants. Calculate the number of moles that have been asked for you to do. Determine the mole-to-mole ratio. Calculate the number of moles of other substances. Convert the number of moles to grams. Okay, so I have nitric acid and I have barium hydroxide. I know I have an acid and a base. I'm going to make a salt and an H2O. All right, so now we're going to be looking at this in respect, I think, to molarity. All right, balanced equation. Here it is. We balance it first, and y'all trust me that that's balanced. I put a 2 here and a 2 there, so now it's balanced. Okay, so number of moles of nitric acid. What are the numbers of moles of nitric acid? Well, I can use this. M times V equals moles. All right, so 12 molar, was that in our original deal? Did I write that down? 12 molar? Or is that new information I'm giving you? I can't remember my previous. Did it not give you all that information? It was written down. It's written down in your book somewhere. I should have written down the actual thing. If I have 12 molar HNO3 and 10 liters of HNO3, and I'm going to get up with it. So that's going to give me my moles of HNO3. So now I know my moles of HNO3, and now I can find my number of moles of BaOH by doing this using my stoichiometric coefficients. Right there. So now I have 60 moles of BaOH2. All right, so it's just a way to get to the answer. I just put a little star right there. If using this, it's like a little bit of a shortcut, cheat kind of a thing. Okay, so you'll have some. We're not finished yet. I think we're gonna convert. Now we have to convert to grams because that's apparently what it asked for. I'm sorry I didn't write that down. 60 over 1 and gives my grams right here. That's from the chart. That should be pointing to that. So I have 10,300 grams, and now, oops, there it is. That's my answer, 10,300 grams. All right, let's try another one. We're going to be using this again, right up here to the right. Number of moles of solute equals M times V. One way to make sodium sulfate is to go through a reaction of sulfuric acid and NaOH. How many grams of sodium sulfate can be produced if 500 milliliters of a 1.6 molar sodium hydroxide solution reacts with excess sulfuric acid? So here's my thing. I got H2SO4 plus NaOH. It was told to me. It's going to give me a salt plus a water. You had to figure that part out. The salt plus the water. Okay? I know if I have a OH, I'm going to be making water. And I'm probably going to take that 2 and put it right there, right? I'm going to take that 2, put it right there. There it is. And then I balance and I find that I have a 2 there. So now I'm balanced. And now this other information. I have 1.6 moles of NaOH. Over 1. I should say M right there. And then 5,000 liters gives me 0.80 moles of NaOH. Using this equation, number of moles equals M times V. Okay, I'm trying to find the number of moles. That word that says 1.6 moles should say molar. Big M. Molar. Now use this to calculate the number of moles sodium sulfate is produced, okay? Because I can know that from my stoichiometric coefficients. I know now that I have 0.40 moles of NaSO4, and am I going to convert to grams now? Yes, I'm going to convert to grams. Therefore, I need 57 grams of NaSO4, Na2SO4 to convert back, to find out how much I needed. Yeah? So just step by step by step. Just practice those. That just requires practice. It's not really anything new there, except the fact that the acid base makes the salt and water. Okay? All right, acid-base titration. This is one of the other fun parts of chemistry, of acids and bases. Titration is the process of slowly neutralizing an acid or a base of an unknown concentration with the opposite, the acid or base, of a known concentration. And what I do is I literally put in 1 drop at a time and I count the number of drops. We will be doing this next week, and it'll be important for you to be counting the number of drops that you put into, it's probably an acid, I don't know, it's probably an acid. And I'm using an indicator, probably phenolphthalein, and I'll show you a video about this in just a second. It's kind of fun. We'll be working with chem plates next week, and doing our titration in our large well of our chem plate. So we have, in this picture right here, we have a flask with an acid of unknown concentration with an indicator in it. So it's going to be a color, and the base will be dropping in drop by drop, and it'll either change the color to clear or change the color to a color, whatever we're working with. Okay, our indicator will change it. You know, the pH paper is an indicator paper too. It's all about indicators. Okay, so let's watch it. It's kind of fun.
pH indicator I want to show you is called phenolphthalein. Phenolphthalein is probably one of the more common pH indicators we use because at pH 8 or lower, it's colorless, and at pH 10 or higher, it's a deep pink. So an acidic solution is going to be colorless, and in a slightly basic to strongly basic solution, it's going to be pink. This makes a very good indicator for a strong acid, strong base titration, or a weak acid, strong base titration. What I'd like to demonstrate to you is how this would work in a titration. This currently is an acidic solution, it is colorless. I'm going to add dropwise a base solution to show you how a titration may occur. Adding a base, you'll see right away the very vibrant pink, but when I swirl it, the pink does go away. As the pink starts to stay around for longer periods of time, we're getting closer and closer to the equivalence point for this pH indicator. Just a few more drops, I believe. Every once in a while, it's good practice to wash down the outsides of the Erlenmeyer flask with some DI water to make sure all the base gets in there. You see that pink color staying just a little bit longer each time I add a drop of base. Until right now, it is a very, very pale pink that disappeared. The next partial drop is probably going to be my equivalence point. Wash that down. Still another partial. Titrations require patience.
And there it goes. All right, so that's kind of fun, right? So it got to the point where, and so what we'll be doing is be counting our drops. And when we count the drops, it'll tell us. So remember, acids destroy bases. And write down OYO 10. No, that's not right. We're not in module 10, are we? So 9.10 maybe. And then possibly, I'm giving you a hint here, problems 7, 9, and 11 on your practice problem page, which are in the back of your book. Okay, so if those are still the same. All right? And bring your study guide practice problems for next week's quiz over acids and bases and a fun lab. All righty, see you next week.